Let me just make sure this looks good. All right, so here we go. I'll talk you through this first part. So it says to consider the graph of the function f of x equals 2x. Well, we all know what that looks like. It's this solid line right here, right? It's just this solid graph. Y-intercept is 0, slope is 2, right? When we talk about its inverse, a couple things we want to talk about. All that we're doing for an inverse, and you should remember this from algebra, right, is that all we're going to do is we're going to take the x values and the y values, and we're going to switch the two. So all we're doing is switching x's and y values. This symbol right here just means inverse. Okay, that's this f to the negative 1. Okay, that's the symbol for an inverse. It does not mean we're raising it to the negative 1 power. It's just a symbol, a notation that we use. And again, notice all we did is we switched the negative 2 and the negative 4, right? And the negative 4 became the x value and the negative 2 became the y value. And we switched these two to get our inverse. Obviously, 0, 0 was the same. These two got switched and these two got switched, right? As we're comparing the points, again, our answer here would just be that we switched x and y values. And that's what it'll be every single time, thank you, that we're finding an inverse. That's all you have to do is switch your x and your y values. Okay? So if I ask you to find an inverse, one way to do it would be to do a chart of values and to then just start switching. Okay? So if 3, negative 5 is a point on g of x, what point do you know exists on g prime of x? Oh, that shouldn't say g prime. That should say g negative 1. Sorry, g inverse. On g inverse of x. Yeah, we would just switch them, and so it would be negative 5, comma 3. Right? When I look at the graph of these, what do you notice? That they are reflections over what line? Yeah, kind of like the origin, but really it's over this one. So they're symmetric about the origin, which is true. But they're reflections over the line y equals x. So anytime you graph them, your inverse will always be a reflection over the line y equals x. So when we graph a lot of these, we're going to graph that dotted line down the middle, and you'll be able to see that there's indeed a reflection over that line, y equals x. Okay? All right, let's answer a few more questions here. Down at letter C. If h of negative 2 equals, h of negative 8 equals 2, what is h inverse of 2? Negative 8, right? All this is saying is the ordered pair here would be, that's my x value, that's my y value, so therefore if this was my x value, then this would be my y value, right? Again, what observations can you make of the graph? And that's what we just wrote over there, that it's a reflection over the line y equals x. What are a couple of methods that you could use to graph the inverse? So what are some ways you could graph them? Well, one way would be like we did there with the x and y charts, right? So you could do x and y tables, and you could switch all your values, right? Another way would just be to reflect it over that line. And then still a third way would be to find the equation algebraically. And we'll talk more about that as I continue on in the notes here. Okay? So far we'll just start with those two in terms of graphing. All right, letter F. The graph of a function j consists of the straight line segment joining the points negative 2, negative 3, and negative 1, 4. So let's graph that. Negative 2, negative 3, and negative 1, 4. And there's our line segment. And this is the function j. So I just said graph the function j, and now graph j inverse. Well, how would I graph its inverse? Right? If j was negative 2, negative 3, and negative 1, 4, in order to graph j inverse, what should I do with those x and y values? Switch them. So I'm just going to switch the x and y values. So I would have negative 3, negative 2, and over here, switch them, and I would have 4, negative 1. And so I graphed those, -3, -2, and 4, -1. And notice after I graph J inverse that these are definitely a reflection over the line y equals x. Right? That they're just flipped right over that line in a nice reflection. Okay? Questions so far? Again, for inverses, we're just flipping x's and y's. That's all you're doing. All right, so let's try this next one. Let k of x equal x cubed. Okay, well, let's graph it. So we know how to graph our cubic with our nice squiggle. Find the inverse, right? K inverse of x. And then on the same set of axes, graph k of x, which we already did, its inverse, and the line y equals k, or y equals x. All right, so this one's a little different. In this case, I'm going to rewrite this equation that they gave me, but I'm going to rewrite it with y equals x cubed. And now I'm going to find this equation algebraically. I'm going to do the same thing. In order to find the inverse, I'm going to switch x and y. Okay, so I'm now going to get x here equals y cubed. All I did is wherever there was an x, I put a y. Wherever there's a y, I put an x. And now I need to solve for y. So what would I do here to both sides? Cube root it. That works. So I would have y equals the cube root of x. So what does the graph of y equals the cube root of x look like?
No idea.
No idea, right? Well, we could pick some values and plug stuff in and see what happens here, right? This isn't too bad. All right. For example, if I put in, like, I don't know, -8, what would be the cube root of -8? -2. What if I put in the -1 here? What would be the cube root of -1? What if I put in 0, 1, and 8, 2? All right, so let's graph those points. So -8 and -2 is going to be somewhere over here. -1, -1 is that same point. 0, 0, 1, 1, and 8, 2. So what's going to happen is it's going to overlap, but it's going to squiggle the other way. So it's going to squiggle up this way and over that way. Okay? So it still has the same curve, but it squiggles the other direction. And then again, if I graph that line, dotted line down the middle of y equals x, right there, I'm going to see that they are definitely reflections over that line, which is why the squiggle goes the other way. And you could graph these on your calculator, and you could double check them, and you would see, indeed, you're going to get that same thing. Okay? All right, let's keep going with inverses. We kind of got a lot here. There's a lot in this section. So, yeah.
Are we finishing the packet?
Oh, yeah, totally. Here we go. Definition of inverses. We got this. We got this. Okay, so this is my official definition of what an inverse is. Is that two functions, f and g, are said to be inverses of one another, provided that, this is composition, right, which we just did, f of g of x equals x. So basically what happens is they undo each other, right? Basically the f and the g cancel out, and the x just pops back out. So when I act g on it and then I act f on it, it just undoes the other one. Whatever the first function did, the other one undoes it. They cancel each other out in a way, and I just get the x. And same thing here is that if I take g of f, again, they're going to cancel each other out, and it's going to pop that out. Okay, so this is our basic definition of what an inverse is. Now, when we usually write this, we would write it like f of f inverse, like that. We would use the inverse notation instead of f and g. And similarly, I would take f inverse of f of x. Right? And so this is really kind of what we're looking at here. If you already know that they're inverses of each other, this is always, always, always going to be true. Yeah, Ricky?
So is it like if g was x squared and f going to be f of square root of x.
Exactly, because they cancel each other out. And you're right that when you say squaring and square rooting, they're inverses of each other, right? Good idea. Okay, so suppose that f and g are a pair of inverse functions. And this part's really easy. I don't want you to do much work. If 13 is in the domain of g, find f of g. Well, since they told you that they were inverses, f of g of 13, well, look, the f and the g are just going to cancel out. Gone, gone, and my answer is just going to be 13.
I like that.
And you do not have to show any work. Right? And I even, at one point, I had a student a couple years ago, it was my favorite thing ever. He literally put quotes around this. He answered the question, he crossed them out, he wrote the answer 13 or whatever it was, and he literally wrote quotes around it, and he wrote, Mrs. Rodriguez. And I was like, you're the best student ever. Because he literally quoted me. I thought it was great. Anytime you quote me, you get extra points. That's always awesome, okay? But you don't have to show any work. This is like the only time ever where I'll be like, don't show work, okay? Because you really don't have to show any work here. Since I know they're inverses, they're going to cancel each other out, and your answer would just be radical 5, okay? Done, okay? So when you're taking the inverse of itself, right, of a function, you don't have to show the work, and they're going to cancel out.
This is too simple.
Okay, that part's too simple. Let's get a little more complex. All right, it says now verify that they are indeed inverses. So in order to verify that something is an inverse, you have to show both of these are true. So I have to show that f of g of x is going to equal x, and I have to show that g of f of x is also going to equal x. If I can show those two things are true, then I have indeed verified that they are inverses. So this isn't too bad. We just have to plug the one function into the other one. We know how to do this. So in this case, it's f of g. I'm going to take all of g and plug it into f. So I'll get 1/3 of 3x minus 6 plus 2, right? That's this function, 1/3 x plus 2. And when I start to work this out, I end up getting, well, the 3's cancel. 6 divided by 3 is 2. Oh, look at that. It equals x. Okay, pretty cool. So therefore, they are inverses, right? They canceled each other out. They did the opposite. All right, let's try the other one. It should also work out the same. This time I'm going to take f of x and plug it in here for x. So I'll have 3 times the quantity 1/3 x plus 2, and then there was a minus 6. 3x minus 6. Cancel stuff out. This just gives me x plus 6 minus 6. Oh, look at that. Equals x. Check. Okay, pretty cool. All right, I'm going to stop this video and put another one on because it's getting too long.